Hello everyone, welcome back to the channel Code with AKJ. Today is day 51 of solving LeetCode 75 challenge and today's problem is maximum subsequence score. So before we dive in, make sure you like, share, comment and subscribe to this channel so you don't miss any latest update. So let's get started with our problem statement. So the problem statement says you are given two zero-indexed integer arrays nums1 and nums2 of equal length n and a positive integer k. You must choose a subsequence of indices from nums1 of length k. So for chosen indices, your score is defined as the sum of selected elements from nums1 multiplied with the minimum of the selected elements from nums2. Return the maximum possible score, and the subsequence of indices of an array is a set that can be derived from the set 0 to n minus 1 by deleting some or no elements. So we are given two integer arrays nums1 and nums2, both of equal length n and a positive integer k. We need to select a subsequence of indices of length k from both nums1 and nums2. And the score of the subsequence is defined as the sum of selected elements from nums1 multiplied with the minimum of selected nums2. So let's understand the problem statement with this given example. Here I have written both the nums1 and nums2 arrays, which is of size 4, and also the k value, which is 3. And we need to return the maximum possible score, and the score is defined as the sum of selected values from nums1 and the minimum of selected values from nums2. So generally, to find the number of subsequences of length k for a n-sized array, the formula would be nck, which is n factorial by k factorial into n minus k factorial. So for this array, the n value would be 4 as the size of the array, and k value would be 3, which is the required length of a subsequence. The number of subsequences for this given nums1 would be 4 factorial by 3 factorial into 4 minus 3 factorial, which is 4. So the number of subsequences for this given nums1 would be 4. And those subsequences are the indices 0, 1, 2, 0, 1, 3, 0, 2, 3, and 1, 2, 3. And we need to find the score of all these subsequences, and out of all these scores, we need to return the maximum possible score. So here I have calculated the score for each and every subsequence. For the first subsequence, which is the index values 0, 1, and 2. So for the 0th index, the nums1 value is 1. The first index would be 3, and the second index would be 3. Same in nums2, that is the 0th index is 2, first index is 1, and second index is 3. So the score is defined as the sum of the selected values from nums1 multiplied by the minimum of the selected values from nums2. So sum here would be 7, and minimum value here is 1. Score would be 7 multiplied by 1, which is 7. In the same way, I have calculated the score for other subsequences as well, which is 6, 12, and 8. And out of all the scores, the maximum value is 12, so we return 12 for this given example 1. So coming to the second example, we have nums1 and nums2 arrays of length 5, and we need subsequences of length 1. So let's again calculate the number of subsequences of length k. That would be 5c1, which is 5 factorial by 4 factorial, which would give us the value 5. So for this nums1 array, there would be 5 number of subsequences, which is generally the each index values. So let's calculate the score for each possible index. So for the index 0, the score would be 4 cross 7, which is 28. And for index 1, the score would be 2 cross 5, which is 10. And for index 2, the score would be 3 cross 10, which is 30. And in the same way, the scores would be 9 and 6. And out of all these possible scores, the maximum possible score here is 30. So for the example 2, our answer would be 30. So this is all about the problem statement. So let's quickly go through the brute force approach. So the brute force approach is straightforward, which is to generate all the subsequence of length k, and we'll calculate the score of all the subsequences, and we'll return the maximum score. So at every step, we'll have two choices, that is to include the current element inside the subsequence or exclude the current element and move forward. So we'll use this include exclude principle to generate all the subsequence of the given array. So we keep on including or excluding the element from the array, and we'll stop once we either picked exactly k elements, and we'll compute the score. And since it is a recursive approach, the base case here would be that if we reach the end of the array without picking the k elements, then we'll return 0. So let's quickly code our brute force approach, and then later on we'll discuss the time and space complexity of our approach. So here's the code for our brute force approach. So we'll start the code by calling the function solve, sending the index value, current subsequence length, the sum value which would be initially 0, and the minimum value which would be initially int max, and sending both the arrays nums1 and nums2 as well as the positive integer k, which is our subsequence length. So let's quickly see our solve function. So for each and every index ind, we decide whether to include this element inside our subsequence or exclude. So if we try to include this nums of ind and nums2 of ind, we'll update our running sum and we'll also find our minimum of nums2. So in case if the element is the first element inside our subsequence, then we'll directly consider nums2 of ind, and if not, we'll find the minimum value out of all the values present inside our subsequence. So while including this element inside our subsequence, we'll check whether we have reached our k length by comparing the current subsequence length with our k. Then we'll calculate our score. And while including this, if we reach at the end of our array, then we'll return 0. So this particular recursive function will give us one answer, as well as we'll also have another option, that is by excluding our current element inside our subsequence. So while excluding, we'll just move on to the next index by sending index +1, and remaining parameters remains the same. So out of these two answers, we'll consider the maximum score by returning the maximum of the both options, that is maximum of both include option and exclude option. So in this way, our recursive function works, where if the index reaches at the end of our array, we'll return 0, which would be our base case. So this is how our recursive function works. So let's quickly run this code. It's working, so let's submit. As you can see, this recursive solution gives us time limit exceeded because of its huge time complexity. So let's discuss the time and space complexity of this solution. So the time and space complexity of the solution would be O of 2 power n in time complexity because of its recursive nature, and space complexity here would be O of n because of the recursive stack. So it's generally feasible for very small n values, that is for n value less than or equals to 20. So we need something better. So let's try to build an iteration step by step. So since our brute force approach gave us time limit exceeded, so let's move on to a better approach. So here we can notice that the score depends on two things, that is sum of chosen nums1 elements and the minimum of chosen nums2 elements. So if we carefully observe that if we sort by nums2 in descending order, at each and every step the current element of nums2 becomes the minimum, that is it becomes a limiting factor. So as we move to the next element while calculating the score, the nums2 value becomes smaller after each and every calculation. So in this way, we'll consider each and every element of nums2 as a smaller number and we'll calculate the score. So here's the approach. So here we'll use greedy plus heap. So the steps of our optimal approach here would be to pair nums1 of I and nums2 of I. And our second step here would be to sort this pair by nums2 in descending order, considering each and every value in nums2 as a limiting factor. And our third step here would be to use min heap, where we'll insert the nums1 values to track the k largest nums1 values. So here, when we try to calculate the score, until or unless the current subsequence length becomes k, and if the current subsequence length exceeds the k value, then we'll try to remove the smallest sum value from the nums1. As we need to maintain the maximum score, we'll try to remove the smallest number from nums1, and hence for that we'll use min heap to track the k largest nums1 values. And for the fourth step, for each index, we'll push the nums1 of index inside our heap and we'll calculate the score. Finally, if the size of our heap becomes greater than k, we'll pop the element from our heap. To understand this approach better, we'll do a dry run on our first example and then we'll move on to our code. So here's the dry run for our first example. So here I've written both nums1 and nums2 as well as the k value 3. So our first step here would be to pair the nums1 of I and nums2 of I. So after pairing, the values would be 2, 1, 1, 3, 3, 3 and 4, 2. And after pairing, we'll sort the pairs by nums2 in descending order. After sorting, the pairs becomes something like this, where 4, 2, 3, 3, 2, 1 and 1, 3 comes in the order. So in our first iteration, we'll take the first pair, that is 4, 2. We'll take two variables, that is sum and score. Both would be initially 0. So we'll first calculate our sum. So our first sum would be 2, and in the meanwhile we'll also push this 2 inside our heap. Coming to the second pair, 3, 3, our sum becomes 5 and we'll push this 3 value inside our heap. Coming to the third pair, 2 comma 1, the sum becomes 6, and we'll also push this one inside our heap. And here you can observe that the k value becomes 3, which means we have reached our first subsequence length, that is k value 3. So at this step, we'll calculate our score. So to calculate our score, the formula which is defined in our problem statement would be the sum of the values of nums1 multiplied with the minimum value of nums2. So here the nums2 value is 2 and the sum here is 6. So the score would be 6 into 2, 12. And now when we move on to the next pair, that is 1 comma 3, the sum here would be 9, and here you can observe that while considering the next pair and pushing the 3 value inside our heap, here the size becomes greater than k, so hence we remove the topmost element from our heap. Since the size becomes greater than k, we'll remove the topmost value and we'll deduct it from our sum. So the current sum here was 9, so we have removed the topmost element, which is 1. So we will subtract this value from our sum, that is 9 minus 1, 8, and we'll calculate our score. So again the score would be the minimum value of nums2 into the sum of nums1. So the sum of nums1 was 8, minimum value of nums2 is 1. So 8 into 1 gives us 8. So after finishing our iteration, the maximum score we have encountered was 12. So for this given example, our answer is 12. So this is how our optimal approach works. So let's quickly code this approach and then later on we'll move on to the time and space complexity analysis. So initially I've taken the size of our nums1 vector. I've considered the vector of pairs where we'll group each and every nums1 of index and nums2 of index together. And after grouping this inside our pairs vector, we'll sort these pairs by nums2 in descending order. Hence the function we have used is rbegin and rend. So after sorting these pairs in descending order by nums2, we'll use a min heap to track the k largest elements. Whenever the size of this min heap becomes greater than k, we'll remove the topmost element, gives us the smallest element, and we'll subtract that value from our sum. I've also taken the max score value, which would be initially min, and the current score value, which would be initially 0. So after iterating over our pairs vector, I've taken both the values, nums2 value and nums1 value. We'll calculate our current sum, which would be current score plus nums1 of value, as well as pushing the nums1 value inside our min heap. And here there would be a check that if this min heap size becomes greater than value k. So if it is greater than k, we'll take the topmost value from the min heap and we'll subtract it from our current sum. And if we reach the current subsequence length, that is if min heap dot size equals to k, then we'll calculate our score and also updating our max score value with the help of this particular statement, which generally takes the maximum out of the current max score with the current generated score, that is current score into nums2 of value. So here, since the return value is in the form of long, I have multiplied this score with 1 long. So in this way, after iterating over our pairs, our max score variable would store the maximum possible score we generated out of all the subsequences of length k. So this is how our optimal approach works. So coming to the time and space complexity, the sorting generally takes O of n log n time complexity, and each heap operation, that is the push operation inside the heap as well as the pop operation outside of the heap, takes O of log k time complexity. Totally, the time complexity of this approach would be O of n log n, which is efficient for n up to 10 power 5. So let's quickly run this code and let's submit. As you can see, the test case is running fine. So let's submit. As you can see, this approach gives a successful submission. So let's quickly move on to the time and space complexity analysis, and then we'll finally summarize the whole problem statement. So we have started this problem statement initially with our brute force approach, where we have used recursion, where for each index int we have to decide whether to include this current element inside a subsequence or exclude it. So we had two options, and for each and every option we had different scores, and we finally took the maximum out of those two options. So that was the recursive approach, which generally took O of 2 power n time complexity in worst case, as we have explored all the subsequence, and hence the time complexity was O of 2 power n. So since we have used recursion, the recursive stack would take the space, hence the space complexity was O of n. And then we have optimized our approach using greedy and heap. So to handle the sum and to make sure we have the maximum sum, we have used heap, where we have tracked the k largest values, and whenever we have reached the subsequence value length k, we have calculated the score, and whenever it exceeds the value k, we took the topmost element and we have removed it from our sum, making sure that the sum remains maximum. And to take the minimum value, that is from nums 2, we have used greedy approach by sorting the pairs in descending order, where we are considering each and every element as the limiting factor and considering it as the minimum element and calculating the score. So as we move on to the next element, the value goes on decreasing, giving us the minimum value and the maximum score. So in this way, we have optimized the time complexity from O of 2 power n, which is exponential, to O of n log n. Coming to the space complexity, since we have stored all these pairs inside the vector, the space complexity remains same, that is from O of n to O of n. So in this way, we have solved this question maximum subsequence score, which is a great example of using priority queue. So if you enjoyed this explanation, don't forget to like, share, comment, and subscribe to the channel for more coding solutions and daily updates. So I'll see you in the next video, which is day 52. Until then, keep learning, keep coding. Thank you.